So because this is the last one, I also wanted to tell you a short story. And then after that, then I'm going to invite Claire Parkinson to introduce John. So once upon a time, long after the Big Bang, in the great plains of savannas, African savanna, where John's father grew up until he was at the age of 9, there were animals who were competing. And those animals, I'm going to use two of them. The first one is the giraffe. The giraffe is famous. It's one of the tallest animal we have in the animal kingdom, about 18 feet. And then there is also a Thompson gazelle. So one day they were competing and wondering who can actually beat the other in a game of hide and seek. And you all know, of course, who the winner is. You know, you have a tall guy and a very small guy, about 2 feet. So guess who is the winner? The gazelle won the race. Then they said, well, so don't worry about this, but I'm actually going to be useful to you later on. So I'm going to fast forward to the following day. And both animals are heading towards a water hole. They're looking for water. So the giraffe is moving forward and followed by the gazelle. So in the process, the giraffe actually sees at a distance a danger coming, a danger looming. And he warns his friend. And he tells him, guess what? There's something happening actually in front. So can we, change the route towards the water hole? And then the gazelle says, no, let's keep going. Don't worry about it. And then because the giraffe could see actually, it looked like a cheetah that was coming, he decided actually to change the route and go a different way. But the gazelle continued on its way. Before long, the cheetah ambushed this guy, and then, oh boy, the thing was hungry, went for the gazelle. The gazelle tried to do its own zigzag run. They can even run at 80 kilometers per hour, but that was not fast enough for the cheetah. And then it was caught. The giraffe, from whatever it was not amused and was saying, I wish you listened to me. Okay? And then when he went back to the other animals, he was wondering, what is he going to tell the other gazelle where his friend went? And he told them that, obviously, I saw him being chased by a cheetah, and because of that, maybe he may not come back. So I'm not going to go all the way to the end of the story, but the message from this is that when you have a tall guy, you have to listen to that guy. So today we are lucky we got, in our own culture we'd say, we got a giraffe in the society, so let's give him a round of applause. It's a good job. So let's welcome Claire Parkinson to introduce her.
Thanks, Katevi. Okay, Charles Katevi has just done a great job in thanking all sorts of people. However, the most important person to thank for this Maniac series is Charles himself. This series has been absolutely phenomenal, and it's been his vision that has created it and his hard work that has continued it. So let's have a round of applause for it. Okay, now to John Mather. I would assume everybody in this room knows that John is Goddard's one and only Nobel Prize winner. He won the Nobel Prize back in 2006. It was based on his excellence as a scientist and his excellence as a leader of the Cosmic Background Explorer mission that many people at Goddard were involved in. John has done lots more than COBE, but COBE was certainly a huge highlight, both for himself and also for Goddard. But he's also senior project scientist of the James Webb Space Telescope, which is another major task. But I want to mention one other role before turning it over to John, and that is an extremely different role than being a scientist or being a leader, and that is being a Nobel laureate. Once a person gets a Nobel Prize, as soon as the announcement is made, demands on his time just skyrocket. All sorts of speaking engagements and conversations and media. John has accepted this additional role with such incredible grace and dedication and willingness to give up his time to others that I don't think that Goddard or NASA or the Nobel organization could have had a better Nobel laureate representative than John Mather. So with that, John, we are anxious to hear you tell us about your life.
Oh my golly. I'm feeling it's a little hard to live up to the introductions. But let me start before I forget. We have pictures of the new telescope that I can hand around, and we forgot to do that before. So I'll send that around. There are plenty more if anybody ever needs them, of course. If you come over to Building 29 and look at the big glass, you can see how we're putting it together.
There's also a book here. Also, he has 3 copies. So if you want one for his first books, then
well, they're not free. I have to sell them, but Anyway, I would like to tell them some stories. And as I was thinking about what to say, I thought this is actually a day of Thanksgiving, which is only next week. But everything that I have to tell you is a kind of thanks. So I'm just so astonished at where humanity has gotten, where I have arrived. Anyway, I was saying that this is a day of Thanksgiving for me to tell stories about who did what and made all of these things possible. And there's no end to how many stories you could tell if you were really to do this. So I sort of have always felt as part of a huge tradition of scientific discovery. And so I made a chart of some of my heroes. These are people that I knew about from high school and grade school even. And by the way, some of us, Archimedes worked for the DOD. Well, there wasn't a lot of distinction between DOD and civilian in those days. But it's sort of a reminder that we're part of a huge context, and that NASA is the civilian arm of some pretty amazing things. We get to do telescopes and a lot of other things, partly as a consequence of the Cold War, which, and for us anyway, did not turn very hot. We were very lucky about that. Anyway, the previous internet, the printing press, was invented a long time ago. It took a while to propagate. From quite early age, I knew about Copernicus and Tycho Brahe and Galileo. When I was about 8, my parents read aloud to my sister and me from biographies of Galileo and Darwin. So they were interested in both of us. My sister didn't turn out to be a scientist. She's something quite different. But anyway, we were exposed, given opportunity to think about and learn about science from very early times. So Newton said we stand on the shoulders of giants, and he couldn't possibly have known all of them that we stand on. I think back to the days when people discovered that if you cooked rocks in the fire, you would get metal. Nobody knows who that was, but everything we do depends on that discovery. So anyway, another hero of mine, Albert Michelson, because I've been using his kind of interferometers all my life, practically. One of the, I guess he is the first American Nobelist, isn't he, in physics? He didn't get his training here, but he did his work here. And so I love what he did. He managed to find ways to those fairly ordinary things that you could build in 1895 to test whether light goes the same speed depending on whether you're moving or not. So he provided us with the evidence that relativity theory was required. Nevertheless, he had something odd to say about discovery. The more important fundamental laws and facts of physical reality have all been discovered, and they are now so firmly established that the possibility of the ever being supplanted in consequence of new discoveries is exceedingly remote. Our future discoveries must be looked for in the 6th place of decimals. There is some argument about whether he really said this. Needless to say, you can track these things down better now than you could. But this was before relativity was discovered, before quantum mechanics was discovered, before nuclear power was discovered, and so, but nevertheless, his 6th place of decimals was the beginning of evidence for some of these discoveries. So it does tell us we don't always know how to predict the future. It was even, I believe, the Wright brothers were quoted as saying we would never be able to fly across the Atlantic. So the people who do it are not always the ones who know what we're going to be able to do in the future. So I have a few speculations, but you can't count on me knowing. So a little bit about how I got into these things. People are always curious about my name because it's a famous name in American history. Well, my particular branch of the family is not that branch. My ancestor, my first Mather ancestor, came from England in 1710, and his mother was unmarried. So we do not know where that Y chromosome came from before that. My dad was a statistician. He worked for Rutgers University, and so he studied dairy cows, and the point was to get more and better milk. Milk with more protein would be a good idea. A long time ago, we bred cows for more butter, and somebody figured out that wasn't so good for us after all. So that was his job, and he had grown up in southern Rhodesia for his first 9 years, and he went into this subject of statistics sort of out of a sense of mission. He saw that the cows in southern Rhodesia were thin, and the ones in the magazines from America were fat. What is this about? So he wanted to know, and so this drew him into animal science. So I learned a little bit from him, not a whole lot, but I learned about statistics. So in 9th grade I had a rat experiment where I had 8 baby rats that lived under the kitchen table for several weeks while we were feeding them different things to see what they liked and didn't like. And so one salient result is cornflakes is not enough for food. You have to have something else. My mother was a first grade teacher, and all of her students learned to read. So if you think that some kids just don't have it, it's not true. They can. They all can. They maybe not have the best start. So there are ways to do it. Her father was a bacteriologist, and he got his PhD in 1922 from Hopkins, the same year my mother was born. So he wanted to be a doctor, but he couldn't afford it, so he got to be a bacteriologist. Then he had this amazing luck of getting to work on penicillin production just at the time that the World War II was coming along, and so he had a wild time with that, I'm sure. I hardly knew him. My sister is a teacher and counselor, and she's my little sister, but she's retired, so she gets to have fun. My wife is Jane, and she's a ballet teacher, so I have her picture coming up. So other people to think about. Just a little bit of history. Schrödinger in 1925 was telling us about quantum mechanics. Goddard in 1926, I think it says, 1926, was inventing the liquid-fueled rocket. And there is, by the way, some of these slides were shown at the Air and Space Museum event we did a few years back. So, and then here is Einstein with Georges Lemaitre. Einstein gave us relativity and the differential equations we would use for cosmology. Lemaitre, by the way, said, you know, Einstein, this idea that the universe is static is not true. And I see how to work out the equations. And he said there was the primeval atom of the early universe. Now, people didn't believe him. Einstein didn't believe him. I don't think he knew that it had already been done before that, 5 years before in the Soviet Union, a brand new Soviet Union by Alexander Friedman, who died only 3 years after he did this work, and he didn't find out that he was right. Anyway, here they are. By the way, as maybe people know, Lemaitre was a Jesuit priest and scholar, as well as an MIT physicist. So he was definitely qualified to work the math. So Einstein said, as most of you have heard him, this story, your equations are correct, your physics is abominable. Because Einstein was really sure that the universe had to be static. Well, we know. So here's Edwin Hubble at the telescope. This picture doesn't show him with his pipe. I guess almost all other pictures show him with his pipe. So there he is trying to take pictures. In those days, you had to watch the eyepiece to make sure that the telescope would track on the star and then you get sharp images. So he developed the experimental technology to be able to make this plot. This plot is the experimental demonstration that the universe is in fact expanding. 1929. Just a little bit of science here. The dots are galaxies, and on the horizontal direction is how far away did you think they were? On the vertical direction, how fast they're moving, and almost all of them going away. 4 of them are not. One of them that's particularly close by is heading straight toward us, and that's the Andromeda Nebula. It's the one you can see with your eye in a dark sky. So in a few billion years, we're having a fantastic collision coming. So that will be quite spectacular for future astronomers. The rest of them, however, are almost all going away, the speed proportional to distance. This was the first estimate of the age of the universe, 1929. So if any of you who are dealing with the general public need to explain that it's not, quote, just a theory, this is an observation from 1929. It's almost getting towards a century old that we've known the universe is expanding. It's not something we just cooked up because it would be fun to talk about over beer. So other things to show you. A little closer to my own history, here's Lyman Spitzer climbing in the Alps, I believe, in 1946. Lyman Spitzer we think of as the father of modern space astronomy, because I think that's the year in which he wrote about the possibility of space telescopes. And he even wrote about one where you could polish off the surface of an asteroid and make a really big mirror so you could see planets around other stars. Very visionary guy. I think this was for the Rand Corporation. Do you remember? Was that for the Rand Corporation he did that? So, a very imaginative guy. Here's another imaginative guy, Fred Hoyle. Fred Hoyle was aware of the idea of the expanding universe, and that's what he looked like in about 1946, I think. About 1950, he gave the name the Big Bang to the Big Bang, and it stuck. He didn't like the Big Bang. He never did like it. And the only reason that he's not still talking about it is that he died. Some people never give up, and I guess that's got some admirable features. And by the way, people don't usually know that he developed a version which I would interpret as inflation theory that he described in, I think, the mid-60s. So pretty amazing guy. Then here I am, born in 1946, and I don't know what year the picture is, but I'm probably 2 or 3 or something. I look pretty happy that day. So I don't really remember my childhood. The only reason I know I exist is somebody told me I was born. So a few other things to show you. Here are pictures of a couple of the fathers of the Big Bang idea. There's George Gamow with his vapors coming out of the primordial material, the Elam that was called by those guys. Robert Herman and Ralph Alpher were 2 young people working with him, and they developed the math to figure out the temperature of the early universe, and they predicted the temperature we should measure is about 5 Kelvin. We got 2.7, pretty good for only having pencils and slide rules. And so they actually got to come to the launch of the COBE satellite years later, and they were so thrilled to see that their story had been demonstrated to be true. Happened a little later. In the early 50s, people thought there were canals on Mars, and I remember hearing about it, that I went down with my family to the Museum of Natural History in New York City. So we saw the planetarium show, of course, and we talked about canals on Mars, and I saw the big meteorite that stands still there in the museum. And it was all wonderful and mysterious, and hardly anybody knew anything about anything, so everything was to be discovered. You might remember there was Ask Mr. Wizard on TV, a wonderful science program. There were, I think Bell Labs had a whole series of TV programs about science, and it was fascinating. Who could not want to do that? That's how I felt about it. And then this one happened. Sputnik went up, I guess, October 4th of 1957. So suddenly the country said, "You didn't tell us about this." Well, of course, it had been reported at least 25 times in the New York Times that this was going to happen. But people had not taken it seriously. We did not have our own response immediate. There's some stories behind that, by the way. Eisenhower knew that we could fly one, and he was worried that if we did fly one, that the Soviet Union would accuse us of spying overhead. So wait a little while and they'll launch their own, and then they can't make that accusation. So that led to spy satellites of all sorts, which also led to enormous outpouring of support for young scientists. So I was in 5th grade at the time, and so suddenly there were science fairs, opportunities, just things sprang up everywhere. Anybody wanted to do anything about electronics or ham radio or science, or there were some science summer camps, all kinds of stuff turned up for me to do, and my parents made sure I got a chance at them. So, like I say, we have a lot to thank the Soviet Union for, even if we didn't like it at the time, and we were terrified to death. I do remember also being told about this same year that if there was a nuclear bomb attack, we should hide under the desk. I don't know how many people here remember that age, but it was stupid. I think pretty nearly everyone knew that wouldn't work. So where did I go to school? I went to school in Sussex, New Jersey, and I'll show you a little map in a bit of where that is. And so that's when I was in school, my first 8 years there. And I went to another school. A lot of people that you know of went to Newton High School in Massachusetts. But this is the other Newton, one of the other, I guess there are about 40 of them. So I went to the one in New Jersey, and I'll show you a picture of that too. But particularly important for me was that NSF had funded summer schools for science nerdy people. So one in math at Assumption College in Worcester, Massachusetts, which was just a few miles from where Robert Goddard had done his work. And Cornell University in physics. I got to play with relativity and quantum mechanics as just after my junior year in high school. It was just an enchanting experience. I thought, golly, I can sort of do this. Maybe there's a future for me in this. And so this was a really key experience for me that said, yeah, you could really enjoy this. It's so much fun. This was another key experience that says there are some kids that are astonishingly good at math that there's no hope to compete with them. This summer school was full of kids from Bronx High School of Science. And there was one who could play 20 games of chess with his eyes closed and beat you in a few moves. So I thought, I know when I'm outclassed. So I'm not going to do that. Anyway, so pictures of childhood. This is the view from my front yard when I was a child. This is a barn where 20 very large bulls used to live. And the backside, which you can't see, are science labs with chemistry and even radiation detectors. There was a little truck parked down there for civil defense with Geiger counters. My dad had a book about radiation safety, which I read. In this field I stood and I flew my model airplane and it crashed right into that. And that was the end of that one. So this is where they were working on the improving the milk production of the cows of northern New Jersey. So my dad had the records of milk production for 10,000 cows. And so he knew statistics. He was among the first people to use computers for massive data analysis. So I got to visit the computing machines way down at in New Brunswick, where the big university campus was. This is the view of my house when I was a child. Trees, by the way. This is a country full of trees. We were a mile away from the Appalachian Trail, an extremely rural area. A good place for farms, almost totally protected from anything. And so there we are way up in the corner of New Jersey, the Delaware River, Appalachian Trail up there. Very, very quiet spot. Rode the school bus to school. It was about an hour to high school, about a half an hour to elementary school, and that's just about the same kind that I rode. This is the high school. It still looks like that today. This is a modern picture. It's not changed. And this is the town square of Newton, the War Memorial. It's almost unchanged from 100 years ago, I think. Nowadays, there's a huge population growth and big box stores just outside town, and it's really kind of discouraging, but that's prosperity for you. So this was a pretty good place for me to go to school because somehow they had good teachers and good stuff. Anyway, so where did I go from there? Just a little bit of story. This is the founding document of NASA, 1958. We started off. I was still in elementary school when this happened, but we started our space race in a formal way that year. There's Mr. Kennedy. Let me see if I can get.
Why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
So that was my childhood, some of it. I didn't pay a whole lot of attention. I didn't think I would ever be working for NASA. I had no idea. I also didn't know James Webb. That's James Webb the man, who was the man who went up to John Kennedy and said, this is what it takes to go to the moon in a decade. And I like to tell this one story about him. He doubled the budget in the taxi cab on the way to see the president. This is because we didn't have spreadsheets and review boards yet. So he quite well knew that he couldn't trust people that look like us to figure this out, that he knew that the entire future of the nation could be hanging on that number, that he was going to promise the president we would go to the moon. Well, how are you going to get enough to make sure you get there? You want to make sure you don't run out of gas halfway. So he knew that there's a huge amount at stake. So I wasn't paying much attention, but I did see it in Life magazine, which was one of those big things we got. So that was while I was still in high school. Anyway, I went to college, Swarthmore College. It's a beautiful place with trees again. This is what it looks like today. This is where you graduate. A couple of famous Swarthmore astronomers. Nancy Roman, one of the very first, moved into NASA headquarters, and we worked for her for a long time. Another friend of mine, she was at college while I was there, Sandy Faber. Maybe many of you will know her. And I see my friend Ann Thompson is here. She's not an astronomer, but she's here. So anyway, it was a good time to study science at the college. It's a liberal arts college, but I didn't take advantage of most of the liberal arts that you could get there. I did math, physics, and astronomy, and small touches of other things. So I really liked it there, and then I had to go to graduate school. So what happened in 1965? I was a freshman in college when these two gentlemen, Penzias and Wilson, measured the cosmic microwave background radiation. And some people said they were all surprised, but I read about that in George Gamoff's little paperback. So I wasn't surprised. Why is anybody surprised about that? It's supposed to be there. Curiously enough, a lot of the scientific community didn't read the paperbacks. So at any rate, that happened. I thought, no big deal. I went to graduate school. That was not what excited me at that time. The thing that was exciting me then was the discovery of the elementary particles, which were still being discovered one by one. Very, very difficult program. And so I wanted to do more of that. I went to Berkeley, and I got a summer job to help work with Henry Frisch at the Lawrence Berkeley Lab. I had to make a one transistor circuit to switch a 400-volt device, which was controlling a spark chamber. And we were told that if you didn't do it right, you could be killed in this lab, and some people almost were. But what I really wanted to do was I wanted to be Richard Feynman. And people said, I'm sorry, are you independently wealthy? There are no jobs for people like that, even, and Richard Feynman already exists. So, so I went hunting for a research program, and I found Paul Richards, who was working with Charles Townsend and Mike Werner to measure the cosmic microwave background radiation. And a lot of you know that Mike Werner is now at JPL and Caltech and is the Spitzer Project scientist, as well as I think the JPL chief scientist these days. Anyway, so what are we going to do? So this is where I lived, in a house with a tree. With these trees over here, just to the right of the house, we planted when I was a student there. These were the physics buildings at Berkeley. What is it like to be doing physics in 1970? It's different. If you wanted a lock-in amplifier, you got one from the shop. It was huge. It had vacuum tubes. You could set one. You could have a bunch of resistors and capacitors that would choose the frequency that you were going to use. These little new Vistors were brand new, tiny, tiny vacuum tubes, which worked almost as well as JFETs now. So the fast Fourier transform had just been invented. There was no Hewlett-Packard calculator at all. Our advanced computer was a PTP-11 that used paper tape, and we made our detectors by hand, really by hand. People. These are people that I work with. That's me. Paul Richards, my advisor, official thesis advisor. He still looks a lot like that, but he's retired. But he can't stay away from the lab. And Mike Werner, he also was hairier in those days. This is our first project we did. We built a Fabry-Perot interferometer to measure the spectrum of the cosmic microwave background radiation from the ground. There's our detector, our lenses. We had a big pipe. It was about 8 feet long, so we were inside the building. Then there was the outdoors, which was cold outside because we were up on a mountain. And we tried to measure. Well, it wasn't very successful. Well, in the sense that it worked, but it didn't tell us anything very interesting. So the next question was, what do you do better? So my thesis advisor devised this idea, build a Michelson interferometer, filled it up with liquid helium, suspended on 2,000 feet of rope from a very high altitude balloon, send it up 25 kilometers, and see if you can now measure from above most of the Earth's atmosphere. So the answer was yes, we could. However, I had to write a thesis about the device that had failed in flight. So pretty important lesson in risk management. We had done some tests. It was very clear, however, that we were tired of testing. We decided as a group, well, maybe the next test should just be push the button and see what happens when you fly, because we'd never flown anything. So we went to Texas and we launched the balloon payload, and there were 3 different reasons why it didn't work. David Woody, my lab partner, came back and figured out why. He made a cold test chamber, put the whole payload in dry ice, and he found out what didn't work. So the next time, it did work. So I got out of Berkeley with my thesis about a project that didn't quite work, and went off to New York City to become a radio astronomer at the Goddard Institute for Space Studies. There we are. This is a modern picture. Tom's Restaurant, you might know from Seinfeld. I don't think they filmed in the real one, but I had lunch there every day, work day. And most of this building is a NASA facility. But you would never know because there's just one little door over here where the security is. So this is how I got back and forth to work. And this is where I lived, a big apartment building on West End Avenue. And this is what we did for computers in those days. The Goddard Institute had one, and we had one here, I believe. I don't think I ever saw the inside, so I just found this this picture on the internet just to illustrate what it was like in those days. So after I'd been there about 6 months thinking, well, I'm going to be a radio astronomer and trying to do that, NASA had other ideas. So in 1974, NASA called for proposals of new scientific missions for Explorer satellites, and they had 2 rockets available, a small one and a big one. They got 150 proposals about, which is like at least an order of magnitude more than they ever dreamed they would get. This is just 5 years after the Apollo landing, so scientists are hungry, we're full of ideas, and about 12 were chosen out of these 150 proposals. 3 of them were cosmic background radiation proposals. One was the one that I had organized with our colleagues from the Goddard Institute for Space Studies, MIT and Princeton, and here at Goddard in Greenbelt. And this was our team. So some of us are still around. Most of us are retired. So anyway, these 3 teams all submitted proposals. And after a couple of years, NASA headquarters said, okay, we're going to form a team with members of all of those 3, and we'll start a new project. So, by the way, this is what the first concept looked like. I drew this picture in 1974 for our proposal, and we had 4 instruments in mind, but the basic idea is pretty similar to what we ended up flying. A big conical shield, various antennas for receiving microwaves from the sky, a liquid helium tank with a couple of instruments in it, and that was the basic idea. So a little more of the history. This 1976 we started and chose our principal investigators. In about 1979 the decision was made to build it here at Goddard, which is not something we always would do. It was recognized that this was much too difficult to send out on contract, that there was no way you could write a contract to please measure this background radiation. Nobody knew how to design the apparatus, nothing. So and also, considering that you don't know how to do it, there's no understanding of how much work it is. So in those days, it was before full cost accounting had really kicked in, so people just worked on it. Now then, however, because it was an in-house project, it had low priority, so we just waited our turn, and our turn never came for a lot of things. Then in '86, the Challenger blew up. And it was, we had designed the apparatus to go up on a space shuttle. At that point, it was going to be impossible to go. So our project management found a way to take off half the mass of the observatory, and repackage it to go back on the Delta rocket, which was the way it had originally been proposed. And so that was, to me, a miracle, a management miracle, that we could actually do that. It was within about 100 pounds of not being possible, but it was possible. So we went from being at the bottom of the queue, the thing that we would do in-house for fun, almost, to we were going to be the very first payload to fly after the Challenger. So we were. So we launched in November 18th, which is yesterday, right? Day before yesterday, in 1989. So it was 24 years and 2 days old. It took us only a few weeks to get our first spectrum result, and then we kept on working for another 4 years. Finally, we're more or less done. So pictures of people to be thankful for. Here's my postdoctoral advisor at Goddard Institute in New York, Pat Thaddeus. Many of these people, by the way, have given Lindsay lectures here. He was one. He was really expert on molecular measurements of finding the stuff in interstellar space. That's me with my wife, Dave Wilkinson at Princeton with his spouse, Mike Hauser. Here, he hired me at Goddard and also ended up being my best man when I got married to Jane. Ray Weiss at MIT, my colleague, we worked together to figure out the design of the spectrometer. George Smoot from Berkeley ended up being the principal investigator of microwave radiometers. Sam Galkus and Mike Jansen from JPL also worked radiometers. More people. Chuck Bennett became our deputy principal investigator for the microwave radiometers. And Nancy Bogus, maybe many of you know that Al Bogus was the project scientist for the Hubble Space Telescope for a long time. Nancy was at headquarters, and then she came out to become my deputy here at Goddard, working on the COBE. Ed Chang, many of you know because he also worked on the Hubble Space Telescope. Ellie Dweck's a theorist, and he helped us figure out what we had seen. Tom Kelsall worked on the Derby experiment. Phil Lubin on the microwaves. Steve Meyer is now at the University of Chicago. Harvey here is still at Goddard inventing things every day. Tom Murdoch was at the Air Force Lab, and I don't know what he's been doing lately. Rick Schaefer was my deputy. He's retired. Bob Silverberg was on our team, and he's now retired, but when I first was working on the proposal in 1974, I would come down on the train and I'd stay at his house. Ned Wright is now at UCLA. He's also become the PI for the WISE mission, which is recently completed its sky surveys and liberated a huge catalog of detections. Engineering team here, many of you will recognize these folks here, although some have retired now. Most have retired, I think. It took the people had to be a little older than me to make this work. So I think all of the people on this picture have retired. More people, engineering team. Dennis McCarthy I still see occasionally because he's got his own company, and we are called upon to give lessons learned kinds of talks and tell stories like this. Dave Gilman hasn't retired either. I think he's down elsewhere in Langley. Anyway, this is the satellite we finally launched. It looks a lot like the picture I drew in 1974, but it obviously went through a lot of changes to go through its configuration for a space shuttle launch as well as a reconfiguration to a Delta. So it's still up there. It's about 500 something miles up in a circular orbit, and I understand it's still visible if you know when to look. It has to be right around sunset or sunrise when it's the brightest for us. So it had 3 instruments, not 4, but basically the same configuration, a helium tank in the middle, and I'll show you what they did. This was my thesis project on steroids. It had a Michelson interferometer. Thank you, Albert Michelson. The main thing that it had that we couldn't do in a balloon payload was it had an external calibrator. So otherwise the configuration is very similar to my thesis project, but this is special. It means you can produce a black body spectrum, which is what the universe is supposed to have given us, and you put it in the aperture of the antenna, and if you get the same answer, you win. So eventually that was done very, very precisely. I see Dale Fixon here in the audience. He was the person who went from, well, it's about like a black body to it's a black body within 50 parts per million. So Dale, a special thanks to Dale for his ability to do that. If you ever need to figure out anything really complicated and nobody else can figure it out, ask Dale. So these are the people. I was the PI. Rick Schaefer was my deputy. Bob Micheley was the instrument engineer, and Mike Roberto, the instrument systems engineer. Here is our first result. It took us just a few weeks to get this up. This was before we'd even figured out how to calibrate the instruments. So we just made up these little 1% error bar boxes to put on because everything seemed to fit. And I see Rich Isaacman is here also. He was the software team lead that helped us figure this out right away. So I remember one day they came in with an autographed interferogram, and it says, you know, it's working. And I was pretty thrilled. So anyway, when you showed this to the astronomers, they were thrilled too, and they said, okay, maybe the Big Bang Theory is safe after all. We had some really funny measurements before this and some pretty funny theories as well. So if you're a good theorist, you can explain a lot of things. If you're a good experimenter, you know never to believe what you've measured. So anyway, so the previous measurements were all over the map out here. There was a lot of excess radiation out here, and we were all glad when it went away. So anyway, the error bar is now 50 parts per million, and the temperature is 2.725 plus or minus less than 1 millidegree because of Dale's work. Pretty astonishing thing when we never could have promised that, but it was there in the equipment. And it's all because there was a differential design that makes it possible to do that. So that's one of your lessons. If you're looking for lessons, make differential measurements. So Ellie Dweck drew us a cartoon explaining why this was important. I wish you wouldn't keep that darn thermostat at 3 Kelvin. So anyway, for good or bad, the early universe is very simple for us. An extraordinarily simple set of equations describes everything we've been able to see in the early times. Now, where did these come from? I don't know. Anyway, here's the second experiment. This is, again, a differential apparatus. This was to make a map of the entire sky. So what we did was we had two antennas pointing in two directions, 60 degrees apart, and then we spin the apparatus in every possible way. So every possible pair of sky points 60 degrees apart are compared. So you have a mountain, like hundreds of millions of measurements of differences between two parts of the sky, and you feed it through a least squares fitting program, and you get a map of the sky. So after you've chewed on this quite hard to make sure you, again, have not made any serious mistakes, then you get a map. And this is the map, the set of maps that we got in April of '92. So this is the one that Stephen Hawking liked and said it was the most important scientific discovery of the century, if not of all time. What it is a map that shows that the early universe is not uniform, has hot and cold spots that are only a tiny amount different from average, a part in 100,000. So when Stephen Hawking said that, I thought, well, that's very generous. Why do you think it's so important? So now I understand that this now supports our entire story that the early universe had hot and cold spots, density variations, and just the action of gravity operating on the material then is able to produce the universe that we now have. So an extraordinarily simple story that's a lot simpler than it could have been if the previous wrong measurements had been correct. So we're very happy about this. It took us many months to confirm this picture. Ned Wright, who I showed you the picture of before, he was the first one to see the spots because he could make a computer program himself with his own PC that could do what an army of other people could do. So he was the first. Of course, then we couldn't, well, suppose he'd made a mistake. Also, it was a team process, so we had to work it through. So we missed many, many, many months checking that that was a correct result. And you might remember this was the days of polywater and cold fusion. And so we were definitely certain that we did not want to go off half-cocked. So we worked very hard to get that. Now, we still were a little in doubt, but then the WMAP mission was flown. This was conceived by Chuck Bennett, our deputy PI for the DMR on COBE, with David Wilkinson at Princeton. And so it was a joint project of Goddard and Princeton University. And so that's what it looked like. Again, it's, by the way, a differential device. Two identical halves looking out in different directions across the sky. The angle between them is not 60, but it's close. So again, hundreds of millions of measurements to compare different parts of the sky. And they made this map. So again, the cosmic hot and cold spots are confirmed. Most of these little dots are cosmic. The red band across the middle is local, but miraculously enough, they agree. The COBE map agrees with this map where it should. So what can you do with a map like that? You can make a power spectrum. So this is the spherical version of a power spectrum, or basically a Fourier analysis of the hot and cold spots. And what we find is there's a particular size of about 1 degree in scale, which turns out to be a measurement of the effective size of the universe at the time that it became transparent. So that was a wonderful surprise. We didn't even know that this would be there when we made our first concept of flying the COBE. In fact, when we proposed the COBE satellite, there was no serious prediction whatever for what this should be. And Chuck Bennett made a lovely plot of the exponential decay of the predictions for time. Anyway, we finally got there, and now it turns out that every single bump on this curve matters, and they are all beautifully represented by a pretty simple theory that, however, requires you to believe two impossible things: dark matter and dark energy. So if you believe those things, we have now their values from this. And we've quite a nice set of numbers then. So the curious thing is that this thing, the dark energy, which was thought for generations to be zero, is dominant. And the result is that the universe is geometrically flat. If you would take a slice of universe all through 13.7 billion years after the bang, measure the sum of angles of a triangle, it'll always be 180 degrees. So it's geometrically flat. Despite the Einstein's giving us curved space-time, that particular piece of it is flat. So the other weird part here is dark matter, which was also who asked for that sort of stuff. But it's also dominant. In fact, if it weren't there, we wouldn't be here either. So even though you can't see it, taste it, smell it, feel it, see it in any way, we should probably be calling it transparent matter rather than dark. Nevertheless, it's really important to us. Third experiment was this one. It's called the DIRBY, the Diffuse Infrared Background Experiment. Mike Hauser was the principal investigator, and this was to make a map of the sky and infrared wavelengths. So what did they find? By the way, again, this is a differential device. There's a tuning fork chopper here, which compares the incoming sky with the cold interior of the device. So this was able to produce a couple quite remarkable results which are not fully understood even now. The sky is a lot brighter than people knew. If you add up the brightnesses of all the galaxies you can find, they do not add up to everything. And so there's an infrared component to this universe of ours that was unexpected. Well, it's not completely unexpected. We did know enough about it to go looking, but people did not expect it to be this bright. Roughly half of the starlight that's ever been produced has been reabsorbed by dust and turned into infrared. That was a bit of a surprise. So I guess we're running out of time eventually, but I want to tell you a few things about more modern stuff. So this is what the universe looked like for NASA in 1985. NASA got a whole lot of good astronomers together to explain to Congress why we needed 4 great observatories. We needed the Hubble, the Spitzer, the Chandra, and the Compton GRO observatories, because all of these things were open questions. And how did the universe begin? This was before COBE had flown, so there were things that might have been different. Some we can now answer. Big Bang, although now we'll just put the question back a little farther. What was before that? Will we find new laws of physics? Yes, we did. We found dark matter and dark energy for sure, and probably inflation. The inflation theory of the early universe has been tested and confirmed by the WMAP results. How did the galaxies form? Well, the Hubble gave us a big surprise on that. It was confidently predicted that they weren't the way they are by the very best theorists. So how were the stars born? It's still pretty mysterious to us. It happens in dark places where you cannot see. How did life start? Well, we know it started at least once. But are we alone? Probably. Who knows? Good question. We're working on that. How were planets formed? I think in 1985 the general opinion was they were extremely rare, and you'd have to work extremely hard to find them. And it wasn't very long before the first few were being found. How do stars die? We didn't yet know that they would turn into black holes, although we had predictions, and certainly we didn't know that they existed. So coming along to what happens after that, well, in 1993 we were up there repairing the Hubble and making it better. And so we went from this kind of picture to that kind of picture. So that said, okay, Hubble is extremely powerful now, what are we going to do? So only a couple of years later, a committee was formed under Alan Dressler to write a book. And it's called HST, Hubble Space Telescope and Beyond. And if you ever want to be inspired by a committee report, this is one to try. Because they explained to us why we needed to build the James Webb Space Telescope, but they didn't call it that yet, and also to develop the technology for finding the planets like ours. So this mattered to me, although I didn't know it at the time. I didn't even know the committee was working. So I'm sitting here, and just I think it was October 30th of 1995, and I'm thinking, well, I better think of something else to do because NASA's never going to do anything as exciting as COBE again. Maybe I should finally look for a university job, something, well, what am I going to do? I'd already started showing view graphs around to my friends about, well, we should make a deployable telescope because the Spitzer telescope is too small. My friends here, I gave a colloquium to the astrophysics group over in Building 21. People laughed and they said, we'll never do that, that's too complicated. So, okay, well, then we won't do that. So, however, we are doing that. And now it's 6.5 meters across instead of a lot smaller. So I'm going to conclude with some stories about this telescope. So in 1995, I got the phone call from Ed Weiler, who had just been made the Origins theme director at NASA headquarters. And the phone message said, and I wasn't even there when it came, he left a message that said, I need a proposal tomorrow. Would you like to work on this next telescope? Call up John Campbell, he knows what this means. So, of course, I called up John Campbell, he knew what it meant. I was needed to be a study scientist for this new telescope. So at that time, I was working with the WMAP team to think about what to do, and I pretty quickly said, I know what my priority's got to be. They've got that one handled, this one's all new, this will be a lot of fun. What could I possibly want more than to work on that telescope? So I said yes, and we sent our one-page proposal the following day, and we got a few hundred K here at Goddard to start studies. So it lasted for a long time. People were very ambitious and thought it could be done a lot quicker than it could, but this is what we've ended up with. And for those of you who are not astronomers and haven't seen it a lot, this telescope is 6.5 meters, 21 feet across, so it's much more than from floor to ceiling here. This umbrella is much bigger than this room. It's as big as a tennis court. Just imagine Roger Federer running back and forth, jumping across the fence in the middle. And it is now an international partnership, which was, by the way, instruction from Ed Weiler. It should become an international partnership. We knew that it had done very well for the Hubble to be an international partnership, so now we have. So European and Canadian space agencies are chipping in. So we've got instruments coming from around the world. By the way, all 4 of them have now arrived. If you come up to Building 29, you can look through the big glass and see what we're doing. You can't actually see the instruments this week because 2 of them are in the big vacuum tank and 2 of them are hiding in the corner. So, but we will be able to see people working in there. Operations are to be at the Space Telescope Science Institute as they are for Hubble. And we're launching in 2018 on a European supplied rocket, the Ariane 5, which, knock on wood, has 50 in a row good launches. And we are planning for operations of 10 years, at least, carrying fuel for that. So in view of giving thanks, some pictures again for people that really made some important things happen. James Webb, the man, we named it after him. It's the first time we have named a telescope after somebody who wasn't an astronomer. And so when this was first proposed from NASA headquarters, astronomers didn't like it. I think many of us were too young to know who James Webb was and what he had done. If you want to know about him, there's a wonderful book called Powering Apollo by a proper historian. And so James Webb, the man, is much more astonishing than you could possibly imagine. I think there's probably no other person in the world that could have made the Apollo program happen. When you read about him, I'm in awe. So Garth Illingworth in 1989, an astronomer, chaired a committee and a meeting, and they wrote a book this thick about what should the new telescope be after Hubble. This is even before Hubble had been launched. Ed Weiler, I told you of already. Alan Dressler, who's the chair of the committee that wrote the inspiring committee report. Dan Golden. Alan Dressler went to see Dan Golden and explained the committee report, and they hit it off. So anyway, Dan, very unusual for administrators, Dan went to the Astronomical Society meeting the following January and announced that Alan's report was good, that it was not nearly ambitious enough. Alan's report asked for a 4-meter telescope. We would build one 6.5 meters or more. And so we were kind of amazed. But peer review kicked in, he got a standing ovation. So that was the thing that began our project to really start rolling. And so immediately people volunteered to work on this project. Engineers all around Goddard, engineers in the various aerospace contractors, astronomers, everybody wanted to participate. So the following summer, we had 3 giant team reports, and all of them concluded, yes, we could really build this project and roughly how to do it. Other people, Peter Stockman was my counterpart at the Space Telescope Institute. He's now retired. 2 chairmen of the Astronomy Society, Bob Kirshner and John Hookra, both helped us gain traction with this. John, I think, even chaired a committee for us for the telescope to help choose the spectrometer. John Campbell was the person who I called up to say, what is this phone call about? And he was our study manager for a few months until we recruited Bernie Seary to take over. Rick Howard, by the way, I put on here, he's was a more recent person at NASA headquarters. When we got our project into trouble, he took on the job of explaining to Congress why we now knew what the right thing to do was. And so we owe him a lot of thanks. It wasn't an easy thing to do. I'm afraid I'll lose my time, so I want to just tell one thing about that. A couple of years ago, maybe 3 years ago, it was recognized that the budget we were requesting was always bigger every year than what we had previously requested. And Senator Mikulski was getting kind of annoyed with us, you could tell. So at a certain point, even though she was thrilled with astronomy, thrilled with NASA, and a very inspiring person to talk with, she said basically, enough, tell us what the real answer is. And so this is a really remarkable story because it enabled NASA to explain directly to Congress what the answer was. Ordinarily, when we have a thing to tell Congress, we tell the OMB first. And OMB says, no, can't tell them that. That's the normal thing to happen. We're not going to ask Congress for that much money. So curiously enough, this letter that Senator Mikulski sent us required us to answer directly. So we did. And so we had to now produce the real answer, the one that doesn't say, well, we can get by with this for this year, but we'll probably have to ask for more next. This was the real answer, including all the possible margin you should ever request, all of the allowance for technical problems, earthquakes, storms, fires, anything that might happen to you. We didn't allow for sequestration and layoffs, but practically everything else we had to allow for. So even a new statistical tool was asserted at this point called the Joint Confidence Level Analysis. And finally, people began to accept it. So eventually Congress, which threatened to kill the project completely, said, okay. And they put us in the budget at the number that we had requested. So Rick was a pretty important part of this process. So many thanks to him. A few other people to tell you about. These are members of our science working group. We are a very widespread international team. Since time is short, I won't tell you very much about them. But about half of them are competitively selected and the other half are ex officio people like me. Many more. Many of us are here at Goddard. A couple of special people at headquarters. Eric Smith was here at Goddard. He was my deputy on this project for a while. He took on the amazing challenge of going to headquarters and making it happen from there. So he is still doing that. Hashim Hassan is a deputy program scientist at headquarters. Our technical leadership here is a very large team, but still not nearly as large as you might imagine. These are the people here who are making this happen, and some of them are not all here. She's in California. He's in Scotland. Let's see, he's in California. He's with the Northrop Grumman contract. So this is a small portion of our team here at Goddard. This is the big model. It does not fly. It's made of steel. And about 150 people here, still only a tenth or so of the worldwide team that it takes to build this observatory. Most of the rest are at the prime contractor and his various subcontractors. The European team is now pretty much finished because they've delivered their stuff, except for the rocket. So I'm actually in there wearing sunglasses. How does the observatory work? It's huge. It's stuffed into the top of the rocket. This is the area, and 5 fairing. There's hardly an inch to spare anywhere. So it's good we didn't actually claim we could build an 8-meter. We are putting it far away where you cannot get there by human travel at any rate. If we ever did need to service this, we would probably have to send in a specially constructed robot. And we know where we would attach it, but we hope we don't ever have to think about it. So our job is to make sure we never need it. So how do we, well, this is our 7 minutes of terror movie. This is the unfolding of the telescope after launch. First the solar panels come out, then the telemetry dish, then the big umbrella, 5-layer umbrella. This, just the movie, is a huge accomplishment. Just as a point on that, when I came here to Goddard, there was a computer in my desk. It was round and it had 2 pointers and it was a slide rule. And I had one already myself. And when people started to design the COBE satellite, they had big pieces of paper and 4H pencils. So that's what it took. You can never have imagined doing something like this with pencils. So this enables us to see things before we build them and see if they would possibly fit together, and to detect things that would go wrong before they go wrong. But there's still also no substitute for test. If anyone should ever tell you, we're going to prove it's true by analysis, tell them no. So finally, it is deployed to the right shape. This all happens within a couple of weeks of launch. It then takes 2 months to coast out to the launch area, to the orbit area, and also to cool down to the right temperature, and then we're enabled to focus it. Now, did I think of this myself? No. When we started thinking about this, we had a meeting at the Space Telescope Institute, and about 15 or 20 people, including a good draftsman, came, and engineers and scientists came, and we mumbled about what it would take and what orbit it should be. And I like to remind people that you just cannot tell how hard it's going to be when you draw a sketch on a whiteboard. Just no way. And when you've got a sketch on the whiteboard, it's easy to make the telescope bigger, make the person smaller. So we didn't know what it was going to take, and we clearly underestimated. But we did learn, of course, from Hubble that we'd better learn how to focus. So this is one of the things we did. We built a scale model. All of these 18 hexagons are adjustable in position and curvature. And there's an algorithm which was derived from the Hubble algorithms that enables us to focus in and make a star image sharp. We also learned from Hubble that an end-to-end focus test was a good idea. And here is the test program we have created. This is at the Johnson Space Flight Center. Apollo astronauts rehearsed into this chamber. And nowadays, we are building a clean room in front of that giant door. So we will have the telescope in there in a few years, verifying that it still focuses when it's cold. It is truly enormous. It's about twice as big in every dimension as our big chamber. And so it makes you dizzy when you get to the top, just to look down. So we'll be there long enough to test it. I'm going to wrap up with just one couple of things more about science. This is the hot topic of today, is planets and transits. We designed our observatory not knowing that this would be a possible technique. But Kepler has found us well over 3,000 candidate objects like this. where a planet goes in front of the star and blocks some starlight, and you can tell how big the planet is. Hubble and Spitzer have both observed these kinds of events. With Spitzer, you can see a warm planet going behind the star and being eclipsed as well. So both of these are really important because they let you study the planets and even not only find out how big they are and how warm they ought to be because of the orbit, but even to do some spectroscopy on the planets themselves and learn whether they're anything like Earth. So with the Webb telescope, we think with a proper target, we might be able to tell if the Earth-like planet we find has water, has enough steam to make an ocean. So very, very ambitious thing, and I think we're very fortunate that we designed something that could do this work, even though it was not in the plan. Just a couple words about the Nobel and all that. I got a phone call on October 3rd of 2006, just a little before breakfast. I was still in bed. The first one was, are you the John Mather that works at NASA? And okay, yes I am. So they wanted to inform me that we're receiving the prize that year. So this is the press release for a discovery of the black body form. The black body form is the curve with the little boxes on it. And the anisotropy, which is Greek, and it means the universe is lumpy. So I got to show this chart a whole heck of a lot. And I got to go get my diploma from the King of Sweden. The physics is mentioned first in Nobel's will, so the physics prize is the first one given, so I'm the first one up. So my big worry is, am I going to trip? Am I going to remember which way to bow? So you're instructed to bow in 3 different directions, first to the king, then to the committee and the royalty behind him, and then to the audience. So I got to talk to the Queen at dinner about her children, and I've been doing this a lot now. As Claire mentioned, I do a lot of public outreach. Just a couple words about what's coming next. A few years ago, this cartoon came out. Everything we know about the universe is wrong, and here's an example. These lads discovered that the universe is accelerating, and this was the discovery of the dark energy. This was a 1998 discovery using the Hubble Space Telescope, and they finally got their Nobel 2 years ago for doing this. So I like to put this in a cultural context, which is Jefferson's. Jefferson wrote in the Declaration of Independence about the laws of nature and of nature's God, and then he talked about these human being things. We hold these truths to be self-evident. And we scientists have an interesting challenge to go from the first to the second. So I think we're part of this process, but we are only a small part. So thanks very much for coming. I have many more stories to tell you, but it has been a pleasure to be here today. Thank you, Charles.
Yeah, because of time, I think I'll allow one comment and then we'll thank John one more time and that's it. Comment, question? Yes, please.
Are you planning to point to the James Webb Telescope?
Yeah, I was asking, are you planning to point the James Webb Telescope to Earth?
No, we
look at it as if it's a reference for other planets? You mentioned that
no, actually, so the question was, can we point the telescope at Earth? And the answer is no, we can't point in that direction. We're putting the telescope far away to keep it cold, and if we ever pointed it at the Earth, it would be warm. So, well, there are lots of other planets to look at. All of the ones from Mars outwards we can see.
I asked because I wanted to see, are you going to set it as a reference?
No, we don't have to use that. Okay?
Okay, so
the book, by the way, I have copies of these books in my office. I don't have any today, but if you want to come get them, I have them.
okay.
$10.
Oh.